Welcome to half-life. So what is half-life? In chemistry, it's how long it takes an isotope of an element to transmute, which means to change, into a more stable isotope of that element. This is a process called radioactive decay, if I remember right. And it has lots of other bearings. I mean, we use this in medicine all the time. There are some radioactive drugs. That's not really the big thing. Like you talk about the half-life of a medicine for a reason. When you take a drug, it interacts with your body. Some of it gets canceled out by the various minerals in your body, and some of it gets processed through your kidneys and liver and passes out of you. But you want to keep a certain percentage of that medication in your system. So that's why if you look at the side of a medicine bottle, it'll tell you how often you're supposed to take the drug, and it's based off the half-life of the medicine. Anyways, we're going to do these one primary way. A lot of people will teach half-life with PERT, P times e to the RT, and I've discovered that's a complete disaster. I like to use this version, principal times 1/2 to the T over the half-life time. That's the easiest way to do these things. I swear it is. It doesn't get any easier than that, okay? It does not. It's the easiest way to possibly do these things. All right, now I skipped over some stuff there, but we're mainly going to talk about carbon-14 in our notes. Carbon-14 has a half-life of 5,600 years. That means in 5,600 years, half the radioactive atoms in a sample will no longer be present. They have transmuted into something less radioactive. We assume that this has always been the case. It comes from the sun, so we assume that all living plants and animals have the same percentage of carbon-14 atoms in their body. The reality is it depends on how much sun you got. All right, skeletal remains of a humanoid are found. After careful analysis, there's found to be that the percentage of carbon-14 is 10% that of a modern-day human. Now, this thing died in the past, okay? So initially, just prior to death or being buried, it had 100% of its total carbon-14 atoms, okay? This is your principle. After time, because this thing was buried and dug up, you have 10% left. So we're going to plug into our principal times 1/2 to the T over the half-life time, okay? After time, you're 10%. You were originally 100%. Carbon-14 has a half-life of 5,600 years. It's just from reading the previous page, kids. It literally says 5,600 years. And we're going to do this by hand. We're going to divide out that 100. That's going to give me 1/10. And I'm going to have 1/2 with an exponent of T over 5,600. There are lots and lots of ways of doing this one. Let's just stick with what we know. Let's do log as base for now, and the next one I'll do something else. So I have a base, I have an exponent, which means I have an argument. A log whose base is 1/2, all right, whose argument is 1/10, is equal to T divided by 5,600. There's your setup. It ain't hard. Now, hopefully you know change of base. A log, base B, argument A, can be pushed buttons in a calculator by doing ln of A over ln of B, or log of A over log of B. You just pick your pill. I like ln. So this side right here is going to become the natural log of 1/10 divided by the natural log of 1/2. And it's still equal to T over 5,600. Now, I don't really care how you do this. A lot of kids will push buttons on the calculator right here and then multiply by 5,600. I like to see perfect answers. So I'm going to fix division through multiplication right here. All right, this is a valid answer. That's perfect. And I'll show you what I mean. But it's pretty common for kids just to want to push buttons, in my mind, way too early. We take the natural log of 1/10. I think that's what I had. We divide it by the natural log of 1/2. We get this decimal right here. And then we turn around and we multiply it by 5,600. Bam, there's our time. 18,600, and we'll say 3 years. This is not an exact science. So it's about 18,603 years. Some kids do push the buttons too early on a piece of paper. They round like the nearest whole number because they just don't know how to round right. But 18,603 years old. Now, if you want to be super duper special, because the state of Tennessee sometimes really tries to throw kids for a loop, they would actually write this as 5,600, the natural log of 1 minus the natural log of 10, and that would be sitting pretty over the natural log of 1 minus the natural log of 2. It looks different, doesn't it? It comes from that we expect kids to be able to break apart logarithms using properties. That's where it comes from. I mean, I get it. If I can get it, you can get it. Right? What we say. All right, let's talk about some nukes. The half-life of weapons-grade plutonium-239, is 24,100 years. Find the yearly decay rate. So let's just plug into what we know, okay? Let's just plug into what we know. The amount after time passes is some principal times 1/2 to the t over 24,100 years. I want the yearly decay rate. I'm going to do that by manipulating the exponent. See, this decay rate is something that happens every 24,100 years. I want to know how much do I lose every single year. So when I see t over 24,100, what I actually see is 1 over 24,100 times t. I'm going to move that piece inside. And this has got to be at least the 10th time I've modeled this kind of manipulation with y'all. Doesn't mean you know how to do it because you don't do your homework or you just cheat off AI. But I'm going to move that inside. I am going to have to use technology to take the 24,100 root of a half because, I don't got all day. So let's see what that is. I'm not saying I couldn't do it. I'm just saying this is just a little bit easier to do. All right, now let's carry this decimal on out. I usually say 4 places, but look at the thing. Like, let's go 7 places. 0.999 and 712. Now, this is still a decay problem, all right? Maybe you remember decay, maybe you don't, but the formula for decay was principal times 1 minus r to the t. So all we got to do is just take this thing away from 1. Let's do 1 minus that. I'm going to have a little more accuracy there than what I wrote on paper. Oh, we got scientific notation. That's 2.876 times 10 to the negative 5th. Let's say 2.8761. What that means is I'm going to move that decimal left 5 places, right? So I'm going to have 4 zeros, 1, 2, 3, 4, 2.861 per year. That's the yearly decay rate. I like percentages. I would say 0.002861% per year. All right. Using the original text, suppose 50 tons of leftover plutonium are placed in the storage. How long until there's only 10 pounds of radioactive material left? So this would be your principal. This would be the amount after time. And we're going to use the formula we wrote in the first place, principal times 1/2 to t over 24,100. And that's what we're going to plug into. I'm sorry about my voice this morning. But we have 10. Now, do you know what a ton is? A ton is 2,000 pounds, right? 2,000 pounds. We have 50 tons of this thing. So 50 times 2,000 is 100,000 pounds. All right. Now, kind of the same process we've been doing. We're going to divide out our 100,000. because you have a 0 that cancels. It just becomes 1 over 10,000. So 1/10,000th is 1/2 an exponent of t over 24,100. And then we do some math, kids. That's what we do. Let's see, in the last one, I think I converted this to a logarithm, and then I did change a base, which is fine. Let's just go ahead and keep doing that. It's working. No point in reinventing the wheel. But I do need to teach you the LN technique. All right, so let's go ahead and make this thing a log. We have a base, we have an exponent, and we have an argument. A log whose base is 1/2, whose argument is 1 over 10,000, is equal to t over 24,100. Now, think about your change of base. Again, I'm an LN guy. The natural log of 1/10,000th, sitting pretty over the natural log of 1/2, is t over 24,100. And now I'm going to clear the fraction by multiplying by 24,100. 24,100 natural logs of 1/10,000th, sitting pretty over the natural log of 1/2, is my time. How long it's going to take for this 50 tons of leftover plutonium to decay to 10 pounds. 50 tons of plutonium is a lot of plutonium. We actually process that stuff and make it stable, and then we try to throw it in a nuclear reactor. It's kind of a big deal right now, is reclaiming these old nuclear warheads so that we can use them in the civilian world. Because what else are we going to do with this material? We don't need 4,000 nuclear warheads. 1,000's enough. We'll destroy the world several times over. There you go. 320,234 years. 320, 234. Good stuff, isn't it? And you're learning logarithms. All right, what do we got here? Some medicine. Certain drug has a half-life of 11 hours. You are administered 800 milligrams of this drug. I should probably look up some drugs and actually give them to you. Not the fun ones, anxiety drugs and stuff like that. Write them all and determine how much of the drug remains in your system. All right, so the amount after time passes is simply the principal times 1/2 to the t over the half-life time. And most of you, after watching 2 of these, should be good. The amount after time passes, the principal of 800 milligrams, times 1/2 to the t over 11 hours. Easy peasy lemon squeezy. Determine how much of this drug remains in your system after 16 hours. Boy, it don't get any easier than that. We're just going to put a 16 there and be done. So the amount after time passes is 800 times 1/2 the 16/11ths power, which means we're going to take the 11th root and then raise it to the 16. That's what it means you're going to do. Anyways, we got 800, we got a parentheses, we have 1/2. Going to take the 11th root and then raise it to the 16th power. And there's 292 milligrams left in your bloodstream. So it might be time to redose. I don't know, it just depends on the drug. Convert your hourly model into a minutely model. Okay, so 11 hours would be 660 minutes. Wouldn't it? I think it would be. So let's go ahead and write it like this. 1/2 to the t over 660. And remember, that's minutes now, not hours. Now, if I move that 1/660th inside, I can just feed this thing minutes, which is kind of cool, but kind of also useless. But let's see what 1/2 to the 1/660th power is. I have no idea what kind of useless stuff the state of Tennessee will ask you on your EOC. 0.9990. The amount after time passes is the principal, which was 800 times 0.9990 to the T. And now it's a minutely model, but the minutely model is not going to be as accurate because you rounded. Even if you went out 8 decimal places, it still wouldn't be as good as a perfect number 1/2. Morning, Mr. Hatcher. Let's see. For the purpose of these notes, I'm not going to do the U tries. Might do a couple of them in class, but that's it for these online notes.